Hello everyone, this is the last class of this week. What we have done so far is we have done the formulation for torsion, and that formulation has been demonstrated through some examples. Now, in all the examples, the cross section of the shaft which is under torsion, that cross section was assumed to be simply connected. Okay. Now, but in many situations it may so happen the shaft that which is undergoing torsion, that the cross section is not simply connected, it may be multiply connected domain. For instance, if we take a circular pipe, okay, and which is under torsion, if we take the cross section, then the cross section is no longer simply connected, it is a multiply connected domain. So, what we will see today, if your cross section is multiply connected, then what modification in the formulation that we have already done, what modification in that formulation is required, and of course, after that modification we will have that modification will be demonstrated through one example. So, today's topic is the torsion formulation for and of course, with an example for multiply connected cross section. You see, if you recall, when we discuss about, okay, this is the shaft which is subjected to torsion and the domain is multiply connected. Now, if I take any cross section in the domain, any arbitrary cross section here, and that cross section is essentially this. Okay. Now we want to do, and this cross section is subjected to torsion. Now, what we want to do is we want to find out what is the relation between this torsion and the angle of twist, what would be the shear stress distribution, what would be the out of plane deformation. That is the same thing that we have done for simply connected domain. You see, if you recall in some of the earlier classes when we were discussing about equilibrium compatibility, that time it was mentioned the compatibility is a compatibility guaranteed your single value displacement field if the domain is simply connected. For multiply connected domain, the compatibility condition is a necessary condition, but may not be sufficient condition. And if you recall, when we talk about circular the formulation in polar coordinate, we gave an example where the compatibility condition is satisfied, but still the single valuedness, the uniqueness of the displacement field could not be obtained. Now, the modification required for multiply connected domain in torsion formulation lies in this difference. So, let us see how it is to be done. Now, very similar to our usual notion that we are using, this is the cross section, and this cross section is represented as R. This is R, and then these the lateral surfaces, this is S. Okay. Now, since we do not have just one lateral surfaces, we have outer surfaces and we have inner surfaces. In this example, we have just one inner surface, but we can have more than one as well. So, let us say these outer surface is SO. In simply connected domain, we did not have to bother about this. S was just the lateral surface, but here SO is the outer surface, and say S1 is the inner surface. S1, because it is just one internal loop we have. If we have a domain like this, suppose if you take a domain which has this another hole, then we can have, then this will be SO, this will be S1, and this will be S2, and so on. Okay. So, we can have, if it is kth k number of loops we have, then it is generated as Sk, where k is equal to 0 to 0, 1 to n. Okay. So, S0 stands for outer surface, and all other integers indices now stands for the inner loops. Okay. Now, we will see in the formulation we have to do a contour integration. The contour integration will be discussed in slightly details in the next week when you talk about complex variable approach, and there we will see, for the time being you take it for granted, there you will see then if your domain is multiply connected domain, then you can cut the domain and make it because if you see, if you start from this point and if you start from this point without holding your pen, you cannot come to the inner loop. Okay. So, there is no continuity. So, what you can do is you can make it continuous by cutting this plane cutting this entire domain, and this, if this is the cut surface, this is the cut surface. Okay. Then what you can do is, suppose you move from this, side, and then you move from this side and then go this side, and then you move from this side, go this, and then go this side. So, you can complete the entire loop. Okay. And suppose this is C, this is generated as C. Okay. The application of this, the usefulness of this this concept will be discussed in next week when you talk about complex variable approach. Okay. Now, so let us see what is the formulation. Okay. Now, so move on. So this is this just now that we discussed, this is the domain R and this is C. We can cut it, we can make it simply connected by cutting it. We can make the boundary continuous, so that the contour integration over the entire boundary can be obtained. Okay. So this is, if you recall, these are the things when we talk about this equation we derived earlier, that psi has to be constant on the boundary. Okay. And for simply connected domain, that we assume that constant value is 0. Okay. Now, then we also have in the last class we discussed, when we in the displacement formulation, that if W is the outer plane displacement, then outer plane displacement is related to the angle of twist, and this unit normal as this, where if you recall, this is essentially this will be ny, this will be minus, this is minus ny, and this is nx. Okay. So, if you take any small domain here, any small domain, and this is your outward normal n, then this is nx and ny, nx and ny. So, this nx and ny are related to dx ds as this, that we discussed in the last class. So, this is how the displacement is related. Okay. And then we also have, if you recall, the relation between the stress and the displacement as this. So, what we are going to do is, we are going to use these expressions along with the additional expression, which is for multiply connectedness of this cross section, which ensures a unique or single value displacement field. Okay. Now, so you see, the single value displacement field on this domain, if W is the outer plane displacement, then can be obtained by this condition. For the time being, this, as I said, this contour integration, for the time being you can take it for granted. This will be discussed in the next class, complex variable approach. So, we can show that single valuedness of the displacement field can be guaranteed if the displacement satisfies this equation. Now, if this is the equation we have, then if we go to the previous slide and see how the and write this expression of W, substitute this expression of W here, then what we have is this. Okay. Now, so and then this is on S1. For the time being, for demonstration of the example, demonstration of the governing equation, or deriving the formula governing equation, we assume it is just a one loop we have. That is why the integration is over S1 only. Then we will see if we have several such loops, then what would be the necessary modification in that. Okay. So, if this is this is the condition we have, this has to be equal to 0. So, this has to be equal to 0. This has to be equal to 0, right. Now, then what this is, if we again if we substitute the previous expression, that is how the displacement is related to stresses, these two expression, if we substitute in these expression, then the expression what we have is this. Okay. Now, let us see, it has two parts. One is this one, the first one, this is one, and this one. Let us see, let us take two parts separately. This has to be equal to 0, right. That is the condition. Now, let us take two parts separately and then try to simplify them. Okay. So, the expression what we have is, this is the expression we have, right. So, let us take the first part. you see, take any small distance, a small arc on this surface S, and then this is as we already discussed that this will be your this will be dx, and this is minus dx, and this is dy, and this is ds. Okay. Now, then sigma xz dx, sigma xz into this and sigma yz into dy. If we see the equilibrium on this surface, if we have shear stress, and that shear stress is tau. The tau, I am using tau because that is the notation we used for torsion when you in the previous classes, or also in the strength of material when you use torsion, it is the symbol that we use. Okay, but when you remember, when we component wise if we have to write the stress tensor, then the off diagonal terms are represented as sigma ij. Okay, that is the notation we are using in this course, but you can use tau as well. So, this is the shear stress on the tau, then simply by applying the equilibrium condition we can show that this is essentially tau into ds. Okay. So, now if it is this first term is tau into ds. So, the first term is tau into ds. Let us see the second term. If we take the second term is this. Now, if we apply Green's theorem we discussed towards the beginning of this course, and also application of Green's theorem we also discussed in some of the earlier classes. Now, if you apply Green's theorem, which essentially gives you your projecting integration from area to surface, area to boundary, or the volume to the surfaces, okay, from one space to another space. So, if we apply Green's theorem, then this is essentially this, okay. And what is A1? A1 is the area enclosed by S1, okay. So, now this is this. Now, look at this expression, and this expression simply we have this is equal to dx dy and to A1 the integration of dx dy over A1 is essentially the area itself, and therefore, this becomes 2 A1. So, the first expression is tau dx, and the second expression we have first expression is tau dx, and the second expression we have 2 A1. Now, let us substitute these two expression in this equation, and the final equation that we get is this is the final equation we get, because this has to be equal to 0, and then this is the equation we get. Okay. Now, suppose if you have two such loops, for instance, if we have an expression, if you have a domain like this. If you have a domain like this, and you have one loop, two loop like this, several loops we have. So, this is S1, S2, S3, S4 and so on, and this is S0 or SO. So, if we have such loops, then the additional things will be in this equation is this equation has to be satisfied over every loop. This equation has to be satisfied if we go, this equation has to be satisfied over every loop, for every loop, and then finally, if we substitute that, the expression we get is this. So, for sk kth point, it will be this. So, now for every loop, this condition needs to be satisfied. Okay. In this figure, the first figure is k is just 1. Okay. Now, what we have, once we have this expression, now let us see what are the boundary conditions. So, this is one expression, additional expression that needs to be satisfied. This expression directly comes from the condition that we imposed to guarantee single valued displacement field. So, this condition in this case is the condition associated because of the multiply connected of the cross section. Okay. We did not have this condition in case of simply connected domain, additional condition. Okay. Now, so let's now the boundary conditions, these are the, if you recall, these are the traction boundary conditions, all the lateral surfaces, the traction boundary conditions are all the lateral surfaces, these are the traction boundary, all these surfaces, these are the traction boundary condition, and then finally, the boundary conditions what we have mz at the end, this is the if you apply the torsion, and that torsion will be equal to this. Okay. All will be equal to 0 if we take psi vanishing at the boundary. that we have already shown. So, if I substitute expression of tau y and the t y and t x the same way that we did in the previous classes, if you substitute in this expression, and then that final expression will be like this, and recall the additional term we have here is this one. This is the additional term we have because of the multiply connectedness of the domain. This is the additional term, and this has to be done over the all loops that you have in the cross section. Okay. Now, we will demonstrate this expression through an example. So, this is the torsion expression for torsion, how the torsion is related to stress function psi. Now, what we have to do is, once we let us now demonstrate that through an example, but the procedure will be again same. We start with an assumption of psi, but when we assume that psi, the condition is the psi d psi ds has to be equal to 0. So, psi has to be constant, psi you can take at 0, so that it vanishes at the outer boundary. That is the same way we did it for simply connected domain. Once we have expression for psi, then we substitute the condition required, in this case the simply connected, this multiply connectedness condition. We can find out the constant associated with the psi such that these conditions are satisfied. Let us see that. Now, let us take one example like this. This example is taken because we already know the solution of elliptical cross section, but now in this case is an hollow elliptical cross section. We will see at the end, compare the solution of this problem and the solution of elliptical cross section. Now, the outer surface is this, and the inner surface is this, when k is depending on the k, you can increase or decrease the size of this hole. Okay. Now, so let us see. Let us start with assumption of psi. Psi is taken as, if you recall, in the case of solid circular, solid elliptical cross section, psi was taken as, actually psi was taken as like this. Psi was k into x square by a square plus y square by b square minus 1, and then k we determined based on the conditions, and this k, if you recall, it was the k, it was the constant for psi. Now, if I have to do the same thing for, this is for the outer surface, this is for S O, or you can take it psi O. Now, if I have to do it for the inner loop, then that expression will be equal to this. Okay. Now, if you recall, it is very similar. If you substitute just k is equal to if you substitute k is equal to 0 here, then it becomes your psi. This will be very similar to this. Okay. Now, so this is for psi o and psi k we have. Now, let us see what next. Now, next, if you recall, this is the condition that we have, and I leave it to you that if you take this as psi and psi k, please check whether these conditions are satisfied or not. This condition is satisfied or not, and you will check with all the boundary conditions, along with all the boundary conditions, all the traction boundary conditions, and also these conditions, whether they satisfy or not if you take psi and psi k as this form. Okay. Now, the next is, this is the relation between torsion and the stress functions. Now, if we substitute the expression of psi and psi k in this relation and then do the exercise, that the integration over r, then we have an expression like this. Okay. Now, and then this expression finally become this. Okay. If you recall, if you substitute k is equal to 0 here, we should be getting the expression for solid elliptical shaft. We will see that at the end. So, this is for torsion. Now, once we have the torsion, then we can then we have the stress function. From the stress function, we can find out the stresses sigma xz and sigma yz, and from stress we can find out what is the shear stress on the boundary, or the distribution of shear stresses. And then in the same way, once we have the expression of shear stress, we can find out what is the maximum shear stress, at what point the stress will be maximum by differentiating shear stress with respect to the coordinate axis, and determine the coordinate value at which the shear stress will be maximum, and substituting that we get the shear stress like this. It will be maximum at the outer surface, and this is the maximum value. Now, you look at so this is the expression for this problem. Now, let us compare the results of this is the results of solid cross section when your solid shaft. This is the result of hollow shaft that just now we have seen. Now, you see, if you substitute k is equal to 0, in this case we get this value. So, it is very similar to the solution, but with an additional term k, which defines the size of this hole. Now, if you have, please note here, don't get confused with this k, don't get confused with this k and the k used here. K used is an expression. Here k is essentially a dummy index which gives you a summation over the number of holes. Okay, and this k defines what is the size of this inner hole. So, please, this you can take it, you can, instead of k you can take it n, small n, and this is n and n. Okay. This is summation over number of holes, and this defines the size of a given hole. Now, so this is the final expression we have, and you can compare this. Now, this is the same way you can now, once we know the expression of shear stress, then what we have to do, that exercise I leave it to you. Once we get the expression of shear stress, then go back to the first slide. We can substitute the shear stress here in the first equation. The same way we did it for in this equation number 1, we can substitute shear stress, integrate it, get W with an additional constant, not constant, is a function of x, and then use the second equation to evaluate that function, and from that we get an expression for W. Now, I leave it to you, find out the expression of W. These examples are solved. If you take any elasticity book, these are the examples, solution of these are the examples are given in the book, and the steps are also given. Now, I leave it to you, do this exercise, get the solution of W, and then compare the solution of W for in hollow elliptical cylinder, hollow elliptical shaft with a solid elliptical shaft, and then see how are the what are the differences. Okay. Now, depending on the cross section, you can apply the similar equations for different problems, but for different problems your psi will be different, but the equations that we derived, the equations will be same, the steps will be exactly same. Now, with this I conclude this week's lecture. Next week what we see is, next week we'll see another way of solving these boundary value problems in elasticity, and that way is using complex variable approach. So, what we do in next week is we will derive all these expressions that you derived so far, we will derive all these expressions, equilibrium, compatibility, Navier's equation, all these expressions we derived in terms of complex variables, and then see how those equations written in terms of complex variable can be solved. We also see that we will also compare that method, not the solution, the steps involved in that method, and the steps we have done in all these methods. We will see that using complex variable method, many problems which are not that easy to solve using the method so far we have discussed, it will be easier to address them, to find the solution of those kind of domain, those kind of problem using complex variable method. Okay, then see you in the next week. Thank you.